Okay, so as I'm sure you'll recall, the first thing that we're asked to determine is the temperature and enthalpy at each of our states 1 to 4. Now, the position that we have the most information about there is position 2. So right at the top there, we know the pressure of the refrigerant at position 2, and we also know its temperature. The other thing that we know is that it's superheated. So as we go through and determine things such as our temperatures and enthalpies, we're going to be switching between the screen that we have here and the thermodynamic property tables for the R410A refrigerant. If you have access to the thermodynamic properties tables, then you may wish to print those off and have them in front of you for reference. So the first thing that we're going to determine then is the enthalpy of the refrigerant at position 2. Note that we already have the temperature and the pressure, so we're looking for H2. Now, when we refer to our temperature entropy diagram, we can see that at position 2 we have superheated vapour. So we're going to look for the enthalpy of superheated vapour at 2,800 kilopascals and 65 degrees C. So here we have a copy of the thermodynamic properties for Freon 410A or refrigerant R410A. And as we go through this document, there's various information here. The first handful of pages relate to the general properties of the refrigerant. Now, we're not so much interested in this for the time being. What we're interested in is enthalpies, entropies, and the like. So table 1 then, which can be found on page 4 of the document, relates to our saturated refrigerant. So specifically there, when we have wet vapour. But as we've already said, at position 2 we have superheated vapour. So we can skip the table on page 4. Page 5 is a continuation of the saturated vapour. Page 6 is a continuation. Page 7 is a continuation. And then you'll notice that when we get to page 8, it specifies at the top there that we have superheated vapour. Now what we notice right at the top of that table is that in grey we have our absolute pressures in kilopascals. Now recall that our pressure is 2,800 kilopascals. Therefore, this first set of tables, where the absolute pressures are 10 kilopascals to 40 kilopascals, are not going to be suitable. So let's continue. The next page is for pressures between 50 and 80 kilopascals. Next we have 90 to 110. So we need to scroll all the way down until we get to the pressure of 2,800 kilopascals. So you'll notice that there's a lot of pages here because what we're representing is a huge amount of information for this refrigerant at different pressures and temperatures. So here we are on page 26 of the document. Once again, we have absolute pressures. Our pressure is 2,800 kilopascals, and our temperature was specified as 65 degrees C. Note that the left-hand column here is our temperatures in degrees C. What we need to do is to track along and find the enthalpy, represented by H, that corresponds with our pressure of 2,800, which would be anything in this column here, and our temperature of 65 degrees. Well, as you'll see here, there's only one value that corresponds with both that pressure and that temperature, and the enthalpy there is 456.9. So all we've done is we've taken our pressure, we're looking for an enthalpy value, so we know we're tracking down this column here. We know our temperature is 65 degrees, therefore tracking across gives us the enthalpy of 456.9. Whilst we're here, we're also going to make a note of the entropy S, and you'll see why in a moment. So we have our pressure of 2,800, entropy S, and our entropy value is 1.8149. So let's go back to our example and we'll take those two values across with us. So as we said, our enthalpy at position 2 then was 456.9 kilojoules per kilogram. But we also extracted another piece of information, and we extracted the entropy S of the steam at position 2. I'm going to mark this in red because we're going to use this for working. and S2 was 1.8149 kilojoules per kilogram Kelvin. Note the units are different there because when we relate to entropy, the units are kilojoules per kilogram Kelvin, as taken from the tables, and when we're looking up enthalpies, those values are in kilojoules per kilogram. There is a legend at the top of the table that tells us this. So what's the significance of the entropy S at position 2? Well, referring to our temperature entropy diagram, as we said before, we know that the entropy at position 1 and the entropy at position 2 are exactly the same. So what we can write is S1 equals S2, which equals 1.8149. So you might be wondering how that information helps us. Well, if we're going to try and find out a bit more information about position 1, then there's two things we need. We need the pressure, P1, because when we get the pressure at P1, we'll be able to determine H1, because that pressure is going to correspond with an enthalpy for the dry saturated vapour at that pressure. So the first thing that we're going to do then is find P1. Once we find P1, we can find H1, and we can also use that pressure and entropy value to find T1. So the important thing here is we're no longer using the superheated tables, we're using the saturated tables. And the other important thing is that we're looking up an entropy value at or close to 1.8149. So let's return to the tables for R410A, and then we're going to use that information to find T1 and H1. Okay, so we're picking up here on page 4, and the reason we're picking up on page 4 is because this is for our saturated vapour. And recall that the property value that we know is for entropy. We know that the entropy of our vapour at position 1 is 1.8149 kilojoules per kilogram Kelvin. Now, as we see here, we have a value SF and we have a value SG. Well, we also know that position 1 is on our dry saturated vapour curve, so we're going to be referencing the SG column. Now we're going to track down that column until we find our desired entropy value of 1.8149, or somewhere close to that value. So here we're at 0.3, so these ones are no good. Here we're going through the 2s and the 1s, so we're getting closer to our value. So if we stop on this page here, we're looking for an entropy value of 1.8149. Well, what we see here is we have a couple of values. We have a value 1.8147, which is below the value we're looking for. And we have a value 1.8167, which is above the value we're looking for. Let's just scroll up slightly so we can see our headings. Now, the information that we're interested in is our temperature in the first column and our pressure, but it's the pressure of the dry saturated vapour. So basically, we're interested in columns 1 and 3 for those two entropy values. Column 1 then is a temperature of 0 degrees and a temperature of -1 degrees. Column 3 is pressures of 796.5 kilopascals and 771.4 kilopascals. The other property we're interested in is the enthalpy of the dry saturated vapour. So we have enthalpy, we have our dry saturated vapour, noting that that's the fourth column from the right hand side. So once again, tracking down that column, we have two enthalpy values. So in this instance, we can see the values at 0 and -1 degrees C are relatively close, but that wouldn't always be the case. And so what we need to do is we need to use something called an interpolation process. Now, when we carry out an interpolation process, we know that we have an entropy between these two values because our entropy is 1.8149. Therefore, our enthalpy value at position 1 is going to sit somewhere between 422.3 and 422.5. Also, our temperature at position 1 is going to sit somewhere between -1 and 0 degrees. And our pressure is going to sit somewhere between 771.4 and 796.5 kilopascals. Now, for the time being, I'm going to ignore them pressures. The only reason I'm going to ignore those pressures is because the question doesn't specifically ask us about the pressure at position 1 or position 4. We know those pressures are the same, but we can still find out our temperature and enthalpy values without using those pressures. So what I'm going to take back across to our workings is the temperatures of 0 and -1 degrees C, the enthalpies of 422.5 and 422.3 kilojoules per kilogram, noting that the higher value there corresponds with 0 degrees, and the entropy values 1.8147 and 1.8167, this time noting that the higher entropy value corresponds with the lower temperature of -1 degree C. When we transfer this information across, we need to be really careful that our temperatures, enthalpies and entropies align with the correct values. Okay, so in the bottom right hand corner I've sketched a small table. And in that table we have a row for our temperatures, we have a row for our enthalpies, and we have a row for our entropies. So at -1 degrees, the enthalpy was 422.3 and the entropy was 1.8167. And at 0 degrees, the enthalpy was 422.5 and the entropy was 1.8147. When we do linear interpolation, we're trying to find the enthalpy and temperature which correspond with our actual entropy of 1.8149. So there's going to be an enthalpy value that sits here between the two known enthalpy values, and there's going to be a temperature that sits here between the two known temperature values. The reason I've drawn the 1.8149 further to the right hand side is because we can see that 1.8149 is much closer to 1.8147 than it is to 1.8167. Now, when we do linear interpolation, what we need to do is we need to quantify that difference. And you'll notice that I've drawn two small arrows. We have an arrow which represents the linear distance between 1.8149 and 1.8147, and then we have an arrow which represents the total distance. In effect, we're at a percentage or a fraction along that continuum. So the way that we determine where we are on that continuum in terms of a decimal is by finding this distance here. And in fact, I'm just going to remove the other distance from our diagram. So we do the shorter distance divided by the longer distance, and that will give us a percentage. So our shorter distance then is 1.8167 minus 1.8149, which in this case equals 0.0018. And our larger distance is 1.8167 minus 1.8147, or 0.002. So to find the percentage distance from our left-hand entropy value, we need to do the fraction 0.0018 divided by 0.002, which equals 0.9. Now our temperatures are relatively straightforward because we can see that the difference between our upper and lower temperatures is 1 degree C. Well, 1 degree C times 0.9 is just 0.9 degrees C. Therefore, this distance here represents 0.9 degrees C, meaning that our temperature at our given entropy value is actually going to be minus 0.1 degrees C. We know that because we have minus 1 degree C and we're adding on 0.9 degrees C. Now we can do exactly the same process for our enthalpy values. Because the difference between our upper and our lower enthalpy value, 422.5 minus 422.3, is 0.2. Well, if our total distance is 0.2, then 0.2 times our 0.9 equals 0.18. Therefore, in this instance, this distance here must be 0.18. That would give us an enthalpy value of 422.48, but let's keep things simple. Let's keep our enthalpy to one decimal place, 422.5. Now, I appreciate that may seem a little bit complicated, but we had an entropy value at -1 degrees C, we had an entropy value at 0 degrees C, and our entropy value sat in between. What we then needed to establish is where it sat as a decimal between those two values. And we found that it sat 90% or 0.9 as a decimal along that continuum. Once we knew that, we was able to determine the temperature at the given entropy value and the enthalpy at the given entropy value. We're going to be doing this process again throughout this video, so you'll have an opportunity to see this again. But let's make note of our useful information. The useful information, or the new information in this instance, is our temperature at position 1 and our enthalpy at position 1, T1 and H1. Okay, so I've made a note of temperature T1 over on the left-hand side, minus 0.1 degrees C, and we also found our enthalpy value, but rather than using the pressure, which would have been one alternative to determine H1, we used the entropy values. And it made more sense to do it that way whilst we were setting up the table for temperatures anyway. So we found that our enthalpy at position 1 was 422.5. So if we substitute the information there with the enthalpy value, 422.5 kilojoules per kilogram. Okay, now since that was quite a difficult process, let's go for an easy win next. Now the easy win is that we know that the temperature at position 4 equals the temperature at position 1, therefore T4 also equals minus 0.1 degrees C. So we now have T1 and T4 both as minus 0.1 degrees C. We have T2 at 65 degrees, and we have our enthalpy values at position 1 and position 2. So now we're going to focus on position 3. Once we have the enthalpy at position 3, we know that the enthalpy at position 3 and 4 is the same. So how do we find the temperature and enthalpy at position 3? Well, as we said earlier, we know the pressure at position 3. We know that the pressure at position 3 is 2,800 kilopascals. We know that because P3 equals P2. We have a constant pressure process going from 2 to 3 or through our condenser here, 2 to 3. We also know at position 3 we have wet saturated vapour. So what we're looking for then for position 3 is the HF value at 2,800 kilopascals. We'll also use that known pressure in order to determine our temperature. So let's go over to the tables once again for saturated refrigerant or saturated vapour and look up our HF values at a pressure of 2,800 kilopascals. So picking up where we left off, we were working with the saturated vapour tables, and we said the pressures at 0 and -1 degrees were 756.5 and 771.4 kilopascals. But our pressure is much higher than that. Our pressure, in fact, is 2,800 kilopascals. And you'll recall that before we had dry saturated vapour, whereas now we have wet saturated vapour. So we can continue down this column. But note that this time, because we have wet saturated vapour, we're looking up a pressure, but we're looking at the pressure for the wet saturated vapour, denoted by the subscript F. We have a pressure of 2,800, so as we continue down that column, we're looking for a pressure, P subscript F, of 2,800. Well, once again, we notice that we don't have an exact value. There's two values here. 2790.9, which corresponds with a vapour at 46 degrees C, and 2856.7, which corresponds with a vapour at 47 degrees C. So what we can do again is we can interpolate, and we can interpolate between those two pressures to determine the actual temperature of the vapour at position 3. And whilst we're extracting that information, we can also get our enthalpy information. So at 47 degrees C, the wet saturated vapour has an enthalpy of 280.7. And at 46 degrees C, the wet saturated vapour has an enthalpy of 278.7. We know that those are the enthalpies for the wet saturated vapour because at the top we've got the enthalpy columns, and we're looking at the enthalpy H subscript F for the wet saturated vapour. So I'm going to take that information across. We have 46 degrees, 2790.9 kilopascals and 278.7 kilojoules per kilogram for the enthalpy. And at 47 degrees we have a pressure of 2856.7 kilopascals and an enthalpy of 280.7. Note that this time the higher pressure and the higher enthalpy both correspond with the higher temperature. Okay, so we've transferred those values across from the thermodynamics tables, and the fixing parameter, or the parameter that we know at position 3, is the pressure, and we know that the pressure is 2800. This time I'm going to write the 2800 closer to the left-hand side because 2800 is closer to 2791 than it is to 2856. So this time we're trying to find the fraction, this distance here, which we know is going to be less than a half. The way that we determine that fraction is using our pressures and our distances. Our shorter distance this time is 2800 minus 2790.9, and our longer distance is 2856.7 minus 2790.9. Now calculating the value of that fraction, or that decimal, gives us 0.138, accurate to 3 decimal places. So we know we're 13.8% of the way along that line. Now once again, for our temperatures, this is very easy because the difference between our upper and lower temperature is 1 degree. Well, 1 degree times 0.138 is just 0.138. Therefore, the corresponding temperature is 46.138. Now I'm going to keep this simple and express that to 1 decimal place. Therefore, we know the temperature at position 3 is 46.1 degrees. Now, let's do the same for our enthalpies. The difference between our upper enthalpy value and our lower enthalpy value is 2. 280.7 minus 278.7. So 2 times our 0.138 then equals 0.276. So in this case, we need to add 0.276 to our lower value of 278.7 to find the corresponding enthalpy value to go alongside a pressure of 2,800 kilopascals. Well, 278.7 plus 0.276 is 278.976 or 279.0, accurate to 1 decimal place. So now we have our T3 value, 46.1 degrees C, our H3 value, 279.0, and now we can list our remaining temperature and enthalpy values. One thing to note here is that the temperature at position 3, referring to our temperature entropy diagram, is lower than our temperature at position 2. And that's exactly as we would expect, because as we move from 2 to the dry saturated vapour point, the superheated steam is cooling. It's only during the change of state where the temperature's fixed. Okay, let's make a note of T3 and H3 on the left-hand side, and then we can conclude our calculations.